He didn't quite put it like that, but I think that's what he meant. Then you might say, well, some people would say, well, that's not quite fair because the cat isn't just there isolated. It's part of an environment. You have to worry about the environment of the cat. Well, okay, I'm going to worry about the environment then. Here it is. That's the environment. Now, I've got another environment for the other one. If I can find it. Except it's dark, I can't see these things. Here we are, it's over here. No, it isn't. It's gone. This happened to me in a lecture I gave recently too. The environment just disappeared. That can't happen. You just have to imagine the environment. And you have to imagine that all those... here we are. I can pretend it's a different... Yes, it is a different one. There you are. You see, this is the dead cat's environment. And here... No, I'm not doing too well here, am I? Where's the live cat? Here's the live cat. Here's the live cat. And here's its environment. And you'll have to take my word for it, it's different. Okay, then you put the boom splitter in. And here we are. And I ask you, what has that done for you? Well, I put Schrodinger's cat in the wrong way around, of course. But apart from that, how did that happen? Yes, this way. Yes, what has that done for you? Well, you might say, well, not much. Of course, what you're supposed to do is sum over all the different environment states and all that. But why should I do that? It's only because I'm too stupid to know where all the environment has gone. But that's supposed to be the answer, but I don't really think that's the answer. Okay, the answer might be something else. Maybe it has to do with the observer coming along and seeing the cat, you see. And notice that the observer here not only does have a mental state, which is seeing the dead cat, but you might worry about how you describe a mental state quantum mechanically. But you don't have to worry about it because you can look at the expression on the observer's face. The observer's not looking too happy. Okay. So, that's what happens with the dead cat. And here's the live cat. And the live cat's environment, which has probably gone on the floor. No. And never mind. No, here's the environment, yes. Live cat's environment. No, that's not the environment. Let's see. Anyway. You've got the two observers, and I ask you, what good does that do you? I mean, why shouldn't an observer have a perception of a live and a dead cat on top of each other? Well, I don't know, but some people would argue for that. It goes this far, and then somehow the observer becomes split into two possible things and so on. Well, that could be true, I suppose. You need to have a theory of why observers don't see superpositions. Maybe you could have such a theory. I think there's probably a much simpler theory, and that would depend on simplifying this problem. The cat is just making life complicated. After all, the cat, if it's going to be consciousness or something, the cat presumably has its own consciousness, and it might worry about being alive or being dead or something. So, what's happened to my machine here? You can see I did this a little hastily, and I haven't. There was supposed to be a detector there, and it's gone. I think you're going to have to imagine that as well as the environment. Without the cat, there's a detector sitting there, but without the gun, it should be just sitting there. I think I'm trying to combine transparencies from two lectures. I think that's the trouble. And the other one had a detector drawn in there, but never mind. The point is that it moves a lump of material from one place to another. And you therefore have to consider the lump is in a superposition of two places. And theory tells us that standard quantum mechanics tells you that you would have a state. If no observation, whatever that means, takes place, you have to consider there's a superposition of that lump in two places at once. You never see such things. Is that because we somehow go down different routes of a multi-universe or something? Or is it because of some theory which goes beyond quantum mechanics, which is inconsistent with present-day quantum mechanics, but to which present-day quantum mechanics is a marvelous approximation. Now, I believe that one can support an idea that when the gravitational field of the lump, or lumps, whatever you call it, the lump, it's really only one lump, but it's in the superposition of two places, that lump, its gravitational field, in order to preserve the principles of Einstein's general theory of relativity, and most particularly what's called the principle of equivalence. I can't go into the details of this, but the principle of equivalence says that if you're in free fall, here we have Galileo dropping a big and a little rock, whether he did or not in practice, from the Leaning Tower of Pisa, and because the big rock and the little rock fall together, the insect on the big rock seems to feel no gravitational field, and the little one seems to hover in front of it, an experience which is now encountered by astronauts. So that the gravitational field can be eliminated by free fall. And if you want that idea to be consistent with the rules of quantum mechanics, and you look at it carefully, you see there's a difficulty. And this difficulty can be removed if you have a scheme something like this, that this superposition is unstable and that it can only last for a certain time, which you can actually calculate, which is Planck's constant over 2 pi, that's what this h cross thing is, divided by a thing Eg. Eg is just the gravitational self-energy of the difference between the distribution here and the distribution there. Let me not go into the details of that, but it's roughly speaking how much energy it would cost you to displace one lump in the gravitational field of the other. As I say, there's only one lump altogether, but think of that as a calculational device. That's the thing Eg, and then this thing represents a maximum lifetime of that object. Now, that is presently just outside what can be done experimentally. There is an experiment at the moment, jointly at Leiden and Santa Barbara, and I think there are other experiments in other parts of the world of a similar nature, which are trying to test to see whether a scheme of this nature could be right. So what I'm trying to say is that quantum mechanics, marvelous though it is limited in its scope at the level that we limited in the scope, although at the level that we've tested it so far, it's come through. But at some point, this would not be the case anymore. And so this is quantum mechanics here, you see. So at all levels, at the certain level when gravitation gets involved, something different is going to start happening. Of course, that could be a big factor if you're considering quantum gravity. So you have to worry that maybe the rules of quantum mechanics aren't going to hold at all levels. And this is something that I think one needs to consider seriously. And it's not the case of any of the mainstream, including, I'm afraid, loop quantum gravity, that any of the mainstream approaches to quantum gravity would certainly have the faith to take quantum mechanics as it is at the moment. Whereas it seems to me there are reasons for believing that here's where you might start to see changes in that subject. Of course, it's sort of pulling the rug from, if space-time structure's got to go and the rules of quantum mechanics have got to go, then where are you going to stand? I mean, it's a bit hard to see what you should be doing, and I quite agree. That's a serious challenge. Nevertheless, it doesn't mean that nature hasn't done that to us. So we have to worry about that possibility. Okay, I'm going back now to the other one that I started, which I haven't really said anything properly about strings. The fact that I haven't got my glasses on means I can't see the time up there either, so I shall just go on into